Today we're talking about one formula and three properties. So this is the change of base formula, and the three properties that we'll be learning about are down at the bottom and on the next page, where we are going to focus on expanding our logarithms. Okay, so this is not a property, it's actually a formula here. So just be careful on the homework problems. Some of them will say to use the formula, other problems will say to use the properties, and when it says use the properties, don't use the formula, okay? But if you do have a formula, the idea is that we could take a logarithm with any base and turn it into a problem that has a common base of 10 or the natural base of e. So what you're looking at here is the subscript, the base, sinks to the bottom, the denominator. But it's not the base anymore, and the value of which you're taking the logarithm rises to the top. Okay, so log base 7 of 4 becomes log of 4 divided by log of 7. So 7 is not the base anymore. So what is the base? Well, it's that common base of 10. We don't even write that, but that's what it would look like. And then you just take that to your calculator. So here's just a simple scientific calculator. It works here as well. Log of 4. Make sure you close that parenthesis before you hit the division bar. And divide by log of 7. So you'll get a decimal value with these types of problems. So 0.712. This strange base of 1/8, we can still handle that here as well. So we have log of 64 on the top, and that's being divided by log of 1/8. All right, so you type that in your calculator, you should get an answer of exactly -2. So that's very handy when we need to change the base. But realistically, today's calculators can be programmed to put in whatever base you need. It has a method for doing that on the graphing calculator. So there it is in case you want to use that. So that's our one formula. Let's go on to the properties. So we're going to kind of make a connection here between some of the properties of exponents that we've seen in the past with the properties of logarithms that we're looking at right now. So you might remember that when we're multiplying a common base, we are going to add those powers, right? So the total would be a to the power of r plus s, whatever those numbers are. So keep that in mind as we take a look at this one. Here you have log of base of a, and it is being taken of r times s. These are your two factors. Okay, factors are things that are being multiplied together. We can expand this out so that each factor gets its own logarithm, right? So now you actually have two terms, log base a of the first factor plus log base a of the next factor. And if you had more factors, you'd have more terms. Now, the reason why these are equivalent is because, remember, this is just an exponent. When you take the logarithm, the answer is an exponent. Again, when you take the logarithm, your answer is an exponent. And what we're doing here is we are adding the exponents. So if you add the answer with the other answer, you're really adding an exponent with an exponent. And that's exactly what we saw here in the exponential form. You are adding those powers. So that's why it works. Here, if you have the natural base, natural log of r plus natural log of s, so you can do it with any base, including the natural base. In exponential form, if you are dividing a common base, you are instead going to subtract those powers. So the exponent on the top minus the exponent on the bottom. So if you have the log of a fraction, we can expand that out. Log base a of the numerator, subtract log base a of the denominator, right? Remember, this is an exponent. This is an exponent. You're subtracting exponents, and that's what we have right here. We're subtracting exponents. It works with the natural base as well. Natural log of r minus natural log of s. And finally, if we have a base raised to the power of r, which in turn is raised to the power of s, what we are doing is we are multiplying those exponents together, r times s. So in logarithmic form, you have log base a of r raised to an exponent. So when you see this pattern, what we're going to do is we're going to take that exponent and bring it to the front as a multiplier. So it's s times log base a of r. So remember, this is just an exponent. The value is an exponent. And the s, hey, that was also an exponent. So we have an exponent times another exponent, and sure enough, that's what we saw in our exponential form. So again, s times natural log of r, that works for that as well. So let's take a look at some examples on the next page. All right, here at the top of the page are those properties presented all over again. We call this the product property because we are multiplying, right? Factors are multiplied together, and when you expand them out, you get a separate term, a separate logarithm for each factor. The quotient property is the result of division, and the power property is, well, you have a power, you have an exponent there. So recall that for every factor, you have to expand it out. So the trick is to keep looking for factors. Here are a few examples. Example 3. Now here it says approximate, which is to say we're going to get a decimal answer, but approximate this. This is the problem, log base b of 10. We want to figure out what does log base b of 10 equal. Well, I don't have a number for the base, so I can't just use like the change of base formula. We're going to be using these clues. They're telling me that log base b of 2 is approximately 0.3562. That's given information. Log base b of 5 is approximately 0.8271. That's given information, but I don't have a log base b of 2. I have log base b of 10, so can we take that 10 and turn it into a 2 instead, or turn it into a 5? Yeah, always look for your factors. So take that 10 and factor it into 2 times 5. Now that you have separate factors, you want to expand them out. So that means you have log base b of 2 plus log base b of 5. Now that's essentially the property. Most of our book problems would stop there, but this problem's a little bit different. They're saying, hey, if you happen to ever encounter log base b of 2, you know its decimal value because we're giving that to you. So we're doing a substitution. Plug in the 0.3562 in place of the log base b of 2. And in case you encounter log base b of 5, which we have, substitute in this value, the 0.8271. So we are adding those results together. So I am using my calculator here just to sum those results. And there's the approximate answer because we have a decimal answer that was approximated for us. Here are some other examples. Number 4, natural log of 6. Now this is saying use those properties, that's what we saw up there, and specifically write each logarithm in this way, in terms of natural log of 2 and natural log of 3. So that means we're not using decimals. Our answer has to look like we have natural log of 2 and natural log of 3. Right now I don't have that. I have natural log of 6. So can you find any factors? And then once you find your factors, expand them out. So natural log of 2 plus natural log of 3. And yeah, we have it. Every term is either one or the other. I should say it's some combination of those. Here's example 5. Natural log of 2 over 27. Expand that out. Natural log of 2 minus natural log of 27. One of our terms looks good, but the other doesn't. We don't want a 27. We either want 2's or 3's in some combination. So the question is, do we have more factors to find? Sure we do. Now, 27 can be factored into 9 times 3, but think about that for a moment. 9 can be factored into 3 times 3. So we really have 3 times 3 times 3. In other words, if at all possible, write your factors in exponential form. If you can't, then you just write 9 times 3. But yeah, 3 cubed is what we want because we can now use that power property to bring that power to the front as a multiplier of its own term. So final answer is natural log of 2 minus 3 times natural log of 3. So our answer is in terms of natural log of 2 and natural log of 3. They're showing up in some combination. All right, let's continue to use the properties to write the expression as a sum or a difference. Those are clues that you need to expand it out with the plus sign or the minus sign, right, as a sum or a difference or even that constant multiple. That's the power property we saw. In other words, we're expanding. So what do? You look for factors. Do you see any factors in problem 6? Log of x cubed times y to the 4th? Yes, factors are being multiplied together. There are your 2 factors, so expand those out. Log of x cubed is added with log of y to the 4th. What's our base? That's just the common base of 10, so we don't need to write the 10. Now we'll use the power property to bring that exponent to the front as a constant multiplier, so 3 times log of x. And that's being added with 4 times log of y. Do we have any more factors? Meaning, are there any more factors inside the logarithm? No. We just have an x. We just have a y. There's no more factors, so we're done. Here's number 7. Do we have any factors here? Sure. 1,000 times y cubed. Can we factor 1,000? That'll be 100 times 10. 100 can factor to 10 times 10. So with 3 zeros, you really have 10 times 10 times 10. You've got 3 10s that are being multiplied together. So let's put that in exponential form. There's my 10 cubed and y cubed. So here are my factors. So let's expand that out. Natural log of 10 cubed plus natural log of y cubed. And it'll bring those powers to the front. Let's see what we have now. 3 times natural log of 10 plus 3 times natural log of y. Are we done? No, we're not. You have to keep looking for factors. Do we have more factors? Yes, 10 can be factored. So this is 3 times natural log of 2 times 5 plus 3 times natural log of y. Y has no more factors, so this term will just sit there the same for a long time. But here we have our 10 factored into 2 times 5. So we have to expand this out. Now be careful. This multiplier of 3 is being multiplied to the entire logarithm. So when we expand this out, we need parentheses, or brackets in this case. So that's what I'm using. So natural log of 2 plus natural log of 5. And then there's the third term, 3 times natural log of y. So now it's completely expanded. And we're done. We could leave it this way. As an option, you could distribute the 3. So 3 times natural log of 2 plus 3 times natural log of 5 plus 3 times natural log of y. But it is completely expanded because there's no more factors. So these two examples, we had factors. Now, we might still have some factors, but now we have the division bar. So this will be our quotient property that we're applying. Log base b of root x all divided by y cubed times z squared. So we do have some factors here on the denominator, but we're going to start by using that quotient property to split up the top from the bottom. So log base b of root x minus log base b of the y cubed z squared. Now one of the issues is we don't want radical signs. We want exponents, right? We like the exponent of 3, we like the exponent of 2, but what's the exponent of the radical? Remember, you can convert that into a rational exponent, meaning a fraction, and if that is a square root, this becomes a power of 1/2. The index becomes the denominator in your exponent. I'm just jotting everything else down the same at this point, just to kind of keep all the steps in sequence here, one step at a time. All right, so we use the quotient property, we change the radical to an exponent. Now we have a bunch of exponents, but we have some factors here. So I'm going to expand right here with the y cubed and the z squared. So log base b of x to the power of 1/2 minus sign. Now again, watch out. That minus sign is subtracting everything that follows. So that means you have to wrap this in parentheses. Log base b of y cubed plus log base b of z squared. Right, so there's our parentheses. Then we'll bring each of those powers to the front of each of their own terms. So 1/2 times log base b of x minus 3 times log base b of y plus 2 times log base b of z. And we're done. As an option, you could distribute the negative sign, but it is fully expanded because we don't have any more factors inside the logarithms. So on this last one here, I recommend that you try it. I would recommend you pause the video, try to work this out, and then turn the video back on and check the answer. So I'm going to pause, I'm going to work out the video, we'll come back here real quick. Alright, I'm going to reveal the answer one line at a time. There are two ways to start, and I'm showing you one way. It's not necessarily the only way or even the best way. What I did was I took that power of 4 on the outside of the parentheses and it brought that to the front. You don't have to do that. As a first step, you could have raised each power to a power. So you could have changed this to a b to the power of 4, x to the power of 20, because 5 times 4 is 20, and y to the power of 4. That's totally fine. You'll get the same answer, and I'll talk more about what that looks like by the time we're done with this. But here, I'm bringing that exponent of 4 to the very front. So what that means is you have to wrap everything in parentheses because it's 4 times the entire logarithm, And if you start expanding, that means it's 4 times everything inside that expansion. So there's my brackets, or parentheses are fine. So here's the numerator, log base b of the numerator, bx to the power of 5. There's the minus sign. There's the denominator, log base b of y. Now here we have some factors. So my next step is I'm going to split up the b from the x to the 5th. So now we have 3 terms on the inside. There's your log base b of b, log base b of x to the 5th, and you're subtracting log base b of y. Sometimes we'll encounter special properties like this one right here. Do you remember what that equals? If the base matches the value of which you're taking the logarithm, that is just 1. Right? So we can simplify when those special properties do show up. I'm bringing that exponent of 5 to the front as a constant multiplier on that middle term. The third term is looking the same. So you could stop here. It is completely expanded. There's no more factors to be found. Or you could distribute the 4 in. So that's what it would look like. So if you had started this problem by originally raising each power to the power of 4, you'd have b to the power of 4, x to the power of 20, y to the power of 4. Notice that what you're seeing here is that the numbers we end up with, these are the exponents on that first step. So this b to the 4th, that's the 4 that you see right here in front. This x to the 20th, that's the 20 you see in front, because we'd be bringing that 20 to the front at some point in our process. The denominator of y to the 4th, again, there's your 4 as well. So you could do it this way if you wanted to. You'll get the same result either way.